Consider a set of finitely many elements. We call the number of elements of the set as cardinality, and the number we get is called a cardinal number. It's therefore an easy task to find the cardinality of a finite set. However, things get interesting once we start dealing with the infinite sets. And just as a side note, the term cardinal numbers are still valid even for infinite sets. For instance, consider the set of all natural numbers. Clearly, it has infinitely many elements. Let's denote its cardinality by this stylish A. Now let's consider the cardinality of real numbers. Again, it contains infinitely many elements, but is its cardinality equal to A? In the language of notations, if the cardinality of the set of real numbers is C, are these two equal? Well, Cantor proved that they are not. In fact, C is greater than A. And interestingly, it's this. This means that there are further classifications of infinite and that some infinites are larger than the others. Like in this case, we can conclude that the number of real numbers are more numerous than the natural numbers. In general, if we have a set and if we can establish a bijection between the set and the set of natural numbers, then we call that set countably infinite, and notationally we call its cardinality Aleph0. We note that it's not possible to establish a bijection between the real numbers and the natural numbers, hence the set of real numbers is uncountably infinite. In fact, its cardinality is equal to the cardinality of the power set of the naturals. Using the previous expressions we encountered, we therefore have C equals 2 to the power of Aleph0. Another important notation that we must care about is Aleph1. In extreme simple words, it's the cardinal number which is just greater than Aleph0. In other words, there aren't any cardinal numbers between Aleph0 and Aleph1. Let's now have a glimpse of the problem whose proof was tried by Cantor for quite some time, the continuum hypothesis. The statement of continuum hypothesis says that we can't find a set whose cardinality is between Aleph0 and 2 to the power of Aleph0. In other words, Aleph1 equals 2 to the power of Aleph0. Also the first of Hilbert's 23 problems, it's a source of numerous debates among mathematicians. A more general statement of continuum hypothesis says that if the cardinality of an infinite set lies between the cardinality of another infinite set and the cardinality of its power set, then the cardinality of the set is either the cardinality of the second set or the cardinality of its power set. It's interesting enough to know that the continuum hypothesis is independent from Zermelo-Fraenkel set theory. Gödel showed that the hypothesis can't be disproven from ZF. On the other hand, Cohen showed that it can't be proven from ZF. Therefore, it became clear that continuum hypothesis is independent of ZF. Gödel believed that the hypothesis is false even though he had shown that the hypothesis is consistent with ZF. This interestingly implies that ZF axioms aren't enough for the universe of sets. Even Cohen believed the falsehood of CH. An interesting viewpoint is that our conception of set is not specific enough to conclude the correctness of CH. Skolem had argued on the same on the basis of a paradoxical statement where from a countable model of ZF axioms we are able to take an uncountable set. The argument was supported by the independence of CH from ZF. To get against the idea, we can demonstrate new axioms to resolve CH in some direction. Some interesting stuffs are associated with the arguments of W. Hugh Woodin, where he gave the concept of star axioms, which implies that 2 to the power of Aleph0 is Aleph2, contradicting CH. However, later he stated that he believed CH to be true. Interestingly, even later, an independent proof came up which supported star axioms. Joel David Hampkins came up with an argument using something called the multiverse approach and argued that continuum hypothesis can't be settled in the manner we are hoping from. Before moving on further, let's have an idea about cofinal subsets of a set. We call a subset B of a set A a cofinal subset of A if for every element A in A, we are able to get an element B in B such that A is less than or equal to B. The function called the cofinality operation is a function which finds the least of the cardinalities of the cofinal subsets of the partially ordered set A. There are some of the identities we get as a direct consequence of the general version of CH. Here, the function CF denotes the cofinality operation. Continuum hypothesis is proven to be insolvable within ZF with or without considering the axiom of choice. The interesting part is that we are assuming ZF to be consistent here. However, we're not sure if this conclusion about the hypothesis is indeed a solution to this problem.